chapter 5, Programming with Linear Algebra. In the last chapter, chapter 4, we studied linear algebra basics. In this chapter, we'll consider popular subjects in linear algebra applicable for real-world problems through programming. Let's go to section 5.1, Determinants. A is an n by n square metric. Then the determinant of the metric A is a scalar value denoted by dta or absolute value sign of A. If A is an 1 by 1 metric having single entry A, then determinant of A is the entry. If A is a 2 by 2 metric having 4 entries, A, B, C, D, then determinant of A is AD minus BC. Okay. We'll try to understand determinant more thoroughly by solving some examples. A is given like this one, 2 by 2 metric, and consider a linear transformation T from R2 to R2 defined by this metric multiplication. Find the determinant of A. Okay, that is the same as AD minus BC. So 2 times 3 minus 1 times 0, which is 6. Right? Okay. Determine the image of rectangle R on the T. Okay, we'll try to solve part B here. Let's visualize R. Okay, that is given like this. Here, there's 0, okay, 0, 0, and this is 2 and 0, and this corner is 2 and 1, and that is now 0 and 1, right? That is R. We want to find the image of R on the T. So we have, okay, another coordinate system here, and we'll try to draw the image here. The metric multiplication is a linear transformation. Linear transformation send lines to lines and points to points, so that here the corners must be corner in the image. So let's try to figure out the image of corners. Then by connecting the corners in this image, we can get the image of this region. Okay. We to order the point, this number 1 corner, and there is number 2, and here there is number 3, and this one is number 4 corner. Okay. Now the metric is here 2, 1, 0, 3. Now for number 1 corner, 0, 0, if we multiply 0, 0, then the result must be 0, 0 here. Okay, we'll write down below of this vector, that one. That means this is the image of the first corner. And corner 2, that is 2, 0, multiply 2, 0 here to the metric A. Then now that means twice of first column, so that must be 4, 0, right? So here we have this is 4, and that is image of the second corner. And I have a third corner, that is 2 and 1. This matrix vector multiplication is row, column, so that is 5, and row, column, and that is 3. So here we have a 5 in x direction, and height is 3. We have here 3, so that is now okay. Here, this point is the image of the third point. Okay, point 4, there's 0 and 1. Once this vector is multiplied here, then that means 0, 1, just the second column. So that is same as here, now 1 and 3. Okay, so we have 1 x direction, and height, that is 3. Okay, that is image of the point 4. Now we connect them to get the image of the region. Start from here, and 2 and 3 and 4, and coming back to 1. Okay, so that's the image of the region R. Okay, now find the area of the image. The bottom length is 4, height is 3, so that must be 12, right? Now figure out how determinant of A, which is 6, the area of rectangle, that is 2, apparently, clearly the area is 2, and the area of the image, that is 12, are related. You can see that 6 is scaling from 2 to 12. 6 times 2 is 12, right? So that in this case, the determinant of A is used as a scaling factor of area. This is not accidental example. It's always happening. So we can say this statement, the determinant can be viewed as a volume scaling factor. In 3D and higher dimensional space, here we deal with volume. We can find the general volume, and so that we can say that this area is a kind of two-dimensional volume, right? So determinant has geometric interpretation like this one, volume scaling factor. Okay. Now we'll try to define determinants for matrices having the dimension larger than or equal to 2 for general n by n matrices. Now we'll begin with the definition of a cofactor. Aij is the submatrix of A obtained by deleting row I and column j of A. Okay, I'll visualize the submatrix. The matrix A is given, then here that is A11, A12, so that is A1n. The below is A21 and go down and AN1. For example, capital A11, the submatrix is obtained in this way. For A11, we delete the row including A11 and column including A11. Then the remainder part must be n-1 by n-1 matrix. That is called A11. In general, here Aij, that is in ith row, that is ith row, and now there is jth column. So we delete ith row, jth column, then remainder part will make again n-1 by n-1 matrix. For this one, we call submatrix Aij. Okay, and we define the ij cofactor of a matrix as the scalar Cij, and defined in this way. So it is a -1 to the I plus j and determinant of the submatrix Aij. So that is cofactor. Now for matrices of n by n entries, here we define the determinant by using the cofactor expansion. Here, determinant of A is A11, C11, and A12, C12, this expansion. So again, we draw the matrix that is A11, A12, and A1n. Then A11 times the corresponding cofactor, so that this cofactor is computed in this way: -1 to the 1 plus 1, which will be 1, and then eliminate here. The A11 is eliminate row, including this one, and column, and this small portion that is n-1 by n-1 matrix. For the submatrix, we get the determinant that will make a C11 by using this definition. And for A12, this entry, we try to get the corresponding cofactor C12 and so on. So for every entry in the first row, we try to get its cofactor, and the entry itself will be multiplied and summed. That is cofactor expansion across the first row. And we define determinant of A is same as the cofactor expansion. Fortunately, we can make such a cofactor expansion not only with the first row, but also across any row and ith row, we can make such expansion. Then the result must be the same. So determinant of A can be gotten by any cofactor expansion across rows, any row. Now again, such cofactor expansion can be done by choosing any column. So cofactor expansion down the column J is defined in this way. In jth column, for this entry, we try to find the corresponding cofactor. For that one, again, go down to the bottom. Then this expansion will be the same value. So we can define the determinant of A by using any of these. Okay. Now find the determinant of A given in this way by expanding across the first row and down column 3. Okay, that is the first task. That is the second task for the example. Okay, let's try to do the first task. Okay, first row. So that is 1 times C11, that is 1 here, plus 5 times, okay, that 5, and C12 plus 0 times C13. Okay, C11 is minus 1 to the 1 plus 1, this 1, 1, and then, okay, the determinant of A11, okay, that is eliminate the row of that entry, row and column. Remainder part is this one, that is the submetric A11, 4, minus 1, minus 2, and 0. Okay, so here this is 1, and that is minus 2, right? Okay, how about C12, which is minus 1 to the 1 plus 2, 1, 2, 1 plus 2, and we have to get the submetric for 5, this entry, and if you eliminate row, column, then remainder part is 2, minus 1, 0, 0, 2, minus 1, 0, 0. Okay, determinant of this metric is 0, so that is 0. Now, this one is 0, so that we don't have to compute to this one because it will make no contribution. Okay, so here from these values, we can get the determinant. 1 times C11 is minus 2, and 5 times 0 is 0, so that is minus 2. We got the determinant when we are using the expansion across the first row. Now let's try to do this one, the second task. Okay, column 3, then, okay, 0 times C13 position, 1, 3, plus here minus 1 is the entry, and C23 plus 0 times C33. Okay, we don't have to worry about C13 because 0 will be multiplied. Also same here, and we only need C23, which is same as minus 1 to the 2 plus 3, and then the determinant of submetric. Okay, for this entry, we have column, row eliminated. Then remainder part is 1, 5, 0, minus 2. 1, 5, 0, minus 2. Right? Okay, that is, okay, this portion is minus 1, and that is minus 2, minus 0, which is minus 2. Minus 1, minus 2. So that must be 2. So from this, here we have first one is 0 plus minus 1 times the C23 is 2, and of course over there will be 0, so that we have minus 2. So we got the same result. Okay, here the observation is that to get the determinant of 3 by 3 metric, and we need the determinant of some matrices. The some matrices are 2 by 2 matrices. So to get 3 by 3 matrices, we combine the determinant of 2 by 2 matrices. That's the first observation. And also second one is that this second task is simpler. And so that once you try to make expansion, coefficient expansion, you may choose a row or column such that that includes most of the zeros. And here in this case, also if you choose a third row, then only one non-zero is there so that you can get the determinant much more effectively, right? Okay. If A is a triangular upper or lower metric, then determinant of A is the product of entries on the main diagonal of A. Okay, let's try to get the determinant of A for this metric, which is upper triangular metric. Okay, now determinant of A, and we are using the coefficient expansion for the first column. Then this only we have 1, and then a C11, that is same as minus 1 to the 1 plus 1, and then determinant of the submetric, that's minus x, minus 7, 5, 0, 3, 0, 0, 0, 4. And for other cofactors, we don't have to worry about. Here, 0, 0, 0 will be multiplied. So they'll make no contribution. Okay. Now, from this one, we have to get determinant of this metric. Again, this position is 1, 1 position, and we try to use the cofactor expansion along with this first column. Then, now there's 1, and this will disappear, and there's a minus 6, and here we'll ignore minus 1 to the 1 plus 1, and then the determinant of this submetric. So there's a 3, 0, 0, 4. Okay. Now we know the determinant of 2 by 2 metric, AD minus BC, right? So that there's 1 times minus 6 times 3 times 4. That's the determinant, which is the product of the entries on the main diagonal, right? Okay. And by using a command, built-in command in MathTalent, you can get it quite easily. Here, A is defined the same metric, and we call dt. Then you can get the answer minus 72. Of course, that will be the same value. The metric A in the last example has a pivot position in each column, so it is invertible. Okay. Now, this metric has here in echelon form, and that is pivot, 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 pivot. In each column, it is pivot, so that it is invertible. Now, one of them is 0, for example. This is 0 rather than 4. Then here that product will be 0, so that determinant will be 0. And then, of course, here, because this is 0 and there are only 3 pivots, so it is not invertible. And so looks like here determinant is 0, then here not, okay, that is not invertible. So in fact, these are the same. So invertible matrices cannot have 0 determinants. Okay. So it's always true. Okay, here we consider properties of determinants. Okay. A is on n by n square metric, and we apply the elementary row operations to the metric and see if how the determinant is changed. B is obtained from A by a row replacement, then determinant of B is same as the determinant of the original matrix. That means replacement is not changing the determinant. Okay, here we apply the replacement and eliminate this value, and twice the subtraction is 0, and twice subtraction will be -5. Okay, for that one, the determinant is AD minus BC, 1 minus X, so that is -5. Okay, now for this one, -5 minus 0, so that again -5. The replacement didn't change the determinant. How about interchange? If two rows of A are interchanged from to form a matrix B, then determinant of B is negation of determinant of A. Now B is made by an interchange. Okay, so first row becomes the second row becomes the first row. For this matrix, the determinant is AD minus BC, 6 minus 1, which is 5. 5 is negation of -5. Right? If one row of A is multiplied by K, so we are applying scaling operation, then for the new matrix, the determinant is K times of the original matrix determinant. Okay, for this matrix, we multiplied for to the second row, K equal -2. Right? So that we have -4 -2. Then from here, the determinant is AD minus BC -2 plus there's 12 minus 12, so it's plus 12, so that the answer is 10. This is obtained from here, that is determinant -5 and times -2, we can get 10. Now you have to be a little bit careful when the K is multiplied to the whole matrix. For example, K is -2, then there will be -2 of A. Okay, for A we are dealing with, that is -2 is multiplied, then -2 minus 6, and then -4 -2, so that determinant of the matrix is AD 4 minus 24, which is now -20. Okay, this value can be interpreted in this way. That is, here -2 squared times -5. That is determinant of A, original matrix. That is now -2 squared. The reason we are putting this way is that here -2A is the same as from original matrix A, we multiply -2 to the first row, and again one more time -2 in the for the second row, so that -2 squared, if we are using this computation, then exactly it can be explained in this way. Okay, so don't be confused with -2 multiplication to whole matrix and multiplication of K to a row. You have to distinguish these two operations. Okay. Okay. Now compute a determinant of A. A is given in this way after applying some elementary row operations. Okay. Now we know how the three elementary row operations change the determinant, so that after applying some elementary row operations, we can get, if we can get the determinant easily, then we can trace back to get the determinant of original matrix. Okay, let's do here. From A, let's try to eliminate this one, replacement. 1, minus 4, and 2. And twice addition will make 0. Twice addition, again 0. Twice addition, that's minus 5. Okay. Now addition will make 0. Addition, there is 3. Addition, there is 2. Okay. And we applied twice of replacement, so that determinant of this one and determinant of this matrix will be the same. Now, we may apply now interchange, and second row and third row will be applied and interchanged. Then 1, minus 4, and 2, and then that is 0, 3, 2, 0, 0, minus 5. Okay, now it is an upper triangular matrix, so that the diagonal entry, their product will be determinant. So the determinant for this matrix is minus 15. Now, after interchange, we got that one. So the determinant, this one must be 15. Now, we obtain this one using replacement operations, so that the determinant of matrix A must be the same as this value. So the answer is 15. Okay. Invertible matrix theorem, we can add one more line for the invertible matrix theorem. A square matrix A is invertible, then it is same as this one. The homogeneous system has only the trivial solution. Now, that is equivalent to say determinant of A is non-zero. Once determinant of A is 0, then if we consider this one as the determinant operation as a volume scaling factor, then here, now once, we assume determinant of A equals 0, then here AX for non-zero, X is a non-zero, and that must be 0, because the volume scaling factor, so it is 0, which means that X will be collapsed to become 0. This means this homogeneous system has non-trivial solution, so it is a kind of a contradiction. And this is a proof, but in linear algebra, in fact, two things are proved in a different way. But also, if you are using the factor that determinant is a volume scaling factor, you can prove the equivalence like here. Okay. A and B are two n by n square matrices. Then here, determinant of A transpose is the same as determinant of A. And that is already we know determinant is minus 5. And for A transpose, again, AD minus BC, so that again minus 5. For every matrix S, for general N, here it'll be true. Okay, for product of two matrices, AB, determinant of AB is the same as determinant of A and times determinant of B. It will be used quite frequently. Here, the determinant of A is minus 5 and determinant of B is 2 minus 4, so that there's a minus 2. Now AB is here, AD minus BC, that is 52 minus 42, which is 10. So you can easily see minus 5 times minus 2 is 10. Right? Now, if A is invertible, then determinant of A inverse is 1 over determinant of A. Okay, we can see it quite easily. Now, A inverse times A must be identity in n dimension, the identity matrix. Now, by using this fact, now determinant of A inverse A is same as determinant of A inverse times determinant of A. Now, right side is determinant of identity. Okay. Earlier, we solved one example saying that for triangular matrices, the determinant is the product of entries on the main diagonal. Now, identity matrix is an lower triangular and upper triangular matrix, so that the diagonal is now 1, so that their product must be 1. So determinant of identity matrix is 1. Now, for determinant of A inverse, we can see easily is 1 over determinant of A. That is exactly this one. Okay. Okay, let's try to solve this problem. Suppose the sequence 5 times 5 matrices A, A1, A2, A3 are related by following elementary row operations. Start from A and with replacement A1, scaling A2, interchange A3, and A3 is given here. So we want to find the determinant of A. Okay, so we start with the determinant of A3. Okay, this is upper triangular matrix. So product of diagonal will be the determinant. 1 minus 2, 3 minus 1, so that is 6, right? The product is 6. Okay, so determinant of A3 is 6, and it is made by interchange operation. So determinant of A2 must be minus 6. Okay, now one row, third row, is scaled by 105, so that A1, determinant of A1 can be obtained by the scale back, which means multiply 5. So here there's minus 30, so that 105 is multiplied, then we can get minus 6. Now that is a replacement operation, so determinant is not changing here. So determinant of A is minus 30. Right? Okay, that's the end of the section. Thank you.